we'll do now is derive an expression for the divergence, the one we already didn't derive, we just stated last time. Show why it is that div v is dvx dx plus dvy dy plus dv dz. And so the idea is, what we do is set up a little rectangular volume. It could be a cube, it could be a rectangle, doesn't matter really, that has its sides parallel to the coordinate axes. So we're in Cartesian coordinates here, and the sides of my little volume here are parallel to the x, y, and z axes. And so we let the point at the center of this guy be x naught, y naught, z naught, and we let the lengths of the sides be dy and dz and dx. So it's a little rectangle whose sides are little differential lengths, small little lengths, dx, dy, dz in the three coordinate directions. And so what we're going to do is consider one particular pair of sides, the ones that are parallel to the yz plane. So if our coordinate axes are on the usual way here, x, y, z, we consider two sides parallel to the yz plane, or in other words, the front side and the back side of this rectangular parallelepiped as I have drawn it. And so, in other words, we're looking at the side for which y and z range over whatever, but x at every point on that side is equal to x naught minus dx over 2. And that would be, I don't know why I call it the front side of my notes, that would be the back side. And the one that has x equals x naught plus dx over 2. That would be the front side, the one that's closer to us there. Okay, so everybody got what we're doing so far here? We're considering the front and the back face of this rectangular parallelepiped. Yes? I know, yeah, I said I don't know why I had that in my notes. Yeah, I've got it backwards in my notes. I know, isn't that awful? Remember, I do have projectiles. Okay, and then for the front side, n hat is sticking out towards us, and for the back side, n hat is sticking out away from us. In other words, n hat being the outward unit normal. This is a cube, it's got an inside and an outside, so therefore we can objectively state which direction is inside, which side outside of that volume. So n hat for the back side is equal to minus x hat, sticks along the minus x direction, and n hat for the front side is equal to just plain x hat, sticks out along the plus x direction. So if we're going to calculate a flux, that's going to be v dot n hat dA for some vector field. So just v dot n hat itself is going to be equal to v sub x, the x component of v, right? Because v dot n hat then in this case is going to be v dot x hat. Now on the front side of the cube here we're talking about. For the front side, v dot n hat will be v dot x hat, so it'll just be whatever vx is, v sub x. So it'll be vx evaluated at x naught plus dx over 2 y naught, I'm sorry, y z vary because over the face of the cube y and z aren't necessarily constant. For the back side, v dot n hat minus v sub x, because n hat is in the minus x direction on the back side. And you got to fix that. I forgot the minus sign. I'm looking at the notes here on the back side there. Okay. Is everybody on board here? I'm seeing kind of blank expressions, so I don't know if you're just tired blank expressions or like what you're talking about blank expressions. All right. But then people started nodding when I asked if people were on board, so I'm going to assume that is the nod of enlightenment. I don't know. All right. So anyway, as long as this little guy is small, we can approximate that v sub x is constant on both of these faces. And in fact, we could approximate that it has the same value as it does at the center of the face. Well, what are the coordinates of the center of the face of the front side? Yeah, the center of the face. In other words, you know, this is like a cube or a rectangular parallelepiped, got a bunch of sides. So consider, you know, this is the point at the center of the cube. So now move out towards this front face here. And so there's a point at the center of that face. What are the coordinates of that point? Yeah, y0 and z0, and what about the x coordinate? Dx over 2, right? Because the center of this thing is at x naught, y naught, z naught. We just said the center of this thing is sitting at x naught, y naught, z naught. So if I want to go to the front face here, the center of the front face, I'm not changing y and z because I'm moving along the x direction if I do that. I'm not changing y and z, so the center of this face has y naught, z naught as its y and z coordinates. And meanwhile, its x coordinate is x naught plus dx over 2 because I've moved half the thickness of the rectangle along the parallelepiped along the x-axis. So x naught plus dx over 2, y naught, z naught are the coordinates of the center of the face. So since our parallelepiped is small, it's really too bad there's not some shorter way to say rectangular parallelepiped, you know. If all the sides are equal, just say cube, but if they're not, you have to say rectangular parallelepiped, unless I'm not remembering what the nice shorter thing to say would be. But in any case, since the parallelepiped is small, v sub x is approximately constant on each face. So therefore, we can say that v sub x is v sub x evaluated at x naught plus dx over 2 y naught z naught on the front side. And same thing, but with minus dx over 2 on the backside. So remember, v is a vector field here. It's something that's a vector that's defined at each point in space. So here I'm talking about the x component of that vector field evaluated at the center of the front and back faces of our little rectangular parallelepiped. And since it's small, we're saying that v sub x is approximately constant over those faces, which is why we can use the value at the center. Okay, any questions? Okay, so we're trying to get an expression for the divergence here, and the divergence is the ratio as the size of this cube goes to 0 of what to what? What's the definition of divergence? Yeah, of course you can look through, but somebody just remember, what's the definition of divergence? Flux over the volume. Yeah, the divergence is the flux divided by the volume. So we need to find an expression for the flux through the surface of this cube, and then we'll divide it by the volume of the cube. What's the volume of the cube? Yeah, the x dy dz is the volume. So now we will write what the flux is. And ultimately, we want the flux through all the faces, but we're considering two of them. So we're going to find the flux through the front and the back faces. So the flux through the front side flux is the integral of v dot n hat dA. But in this case, we're saying that our little rectangular parallelepiped is small, and so therefore we can say that v dot n hat is very nearly constant on that face. Namely, we've already said that v dot n hat is v sub x evaluated on that face. So that'll just be v sub x times v sub x evaluated at x naught plus dx over 2 y naught z naught. Times dy dz. Why did I say times dy dz? That's just the area of the face, right? Yeah, in other words, v dot n hat is that, and then we multiply by dA, the area of the face, which is dy dz. In other words, remember that if v dot n hat is constant on some surface, then the flux through that surface is just v dot n hat multiplied by the area of the surface. The integral becomes very easy if v dot n hat is constant over a surface. It's just v dot n hat can be pulled out of the integral, and you just get the integral of dA, or in other words, just area of the surface, which in this little bitty case here is just dy dz. That's the area of that face right there. And similarly for the back side, v dot n hat dA will be minus v sub x evaluated at x naught minus dx over 2 y naught z naught times dy dz. Minus v sub x because of the fact that on the back face, n hat is in the minus x direction, and therefore vx, or v dot n hat is minus v sub x on that back face. So now, we invoke our buddy Taylor's theorem, which says that if I want to evaluate any function, including, say, v sub x, at x naught plus or minus dx over 2, y naught z naught, well, that's going to be approximately equal to the value at x naught, y naught, z naught, plus the first order correction to that. So this is approximately dx at x naught, y naught, z naught, plus or minus, since I'm accounting for both cases here, plus or minus the first derivative, the first partial derivative, dv sub x dx, evaluated at x naught, y naught, z naught, times dx over 2. So the value on a face is the value at the center plus the derivative times how far you've moved from the center of the cube. The value of on a face, the value on the center of the cube plus first derivative times how far you move to get to that face along the corresponding coordinate direction. Okay? Does this make sense or not? Questions about this? Doesn't make sense, let me know. Okay? So, if we want the net flux from the two sides, we've got to add it up. Side flux plus backside flux. And so we add these two terms, one with the plus, one with the minus. But we have to remember that for the backside, we've already got a minus sign out in front. In other words, the backside is minus v sub x on that side. So front side flux v sub x evaluated at the center of the cube, v sub x evaluated at x naught, y naught, z naught, plus dvx dx times dx over 2, and now I'm not bothering to say where dvx dx is evaluated, but it's at the center of the cube. dy dz. Flux that's v sub x at this coordinate times dy dz, and then we've made this approximation that v sub x at x naught plus dx over 2 is the stuff inside the square brackets here. And then we have to add to that the flux through the backside. The flux through the backside is minus v sub x evaluated at x naught minus dx over 2 y naught z naught. So we add minus v sub x of x naught, y naught, z naught, minus dvx dx times dx over 2, dy dz, and a little space there, so dy dz. And the point is that what happens is that the v sub x's at the center cancel one another out. That's common to both terms. And so they cancel because of the fact that the backside flux has that minus sign associated with it. And meanwhile, we've got dvx dx times dx over 2 plus minus minus dvx dx dx over 2 for a grand total of dvx dx just times dx. Right? Does that make sense? Following that there? Okay. So we just get dvx dx times dx dy dz. Because the dy dz terms were hanging around for the area contributions on both sides. This is the sort of argument you should familiarize yourself with, because this kind of argument is the sort of thing that's used all the time in deriving differential equations, partial differential equations, looking at little tiny volumes and writing down expressions for various quantities and taking limits and saying, aha, this is the expression that I need for my differential equation. So what's going to happen if I did this in the y direction and then the z direction? In other words, what will I get if I did the y faces and then the z faces instead of the x faces? Same kind of thing, right? Except that instead of dvx dx, dvy dy, and dvz dz. So if I do all 6 faces, we'll get similar terms in y and z. Same kind of argument leads to the exact same kinds of terms. And so the flux from that little rectangular parallel pipette, I get tired of writing rectangular parallel pipette, so that's the R car, R par is from henceforth on to be understood as meaning rectangular parallelepiped. Okay? So the flux from the R par is going to be equal to dvx dx plus dvy dy plus dvz dz times dx dy dz. Aha! But what is dx dy dz? That's the volume, yes. This is d tau. The volume of our little R par. I like that. That's so much nicer than saying rectangular parallelepiped. The word for today is R par.
It's not a word.
What?
Not a word.
The new word for today is R par. The other word for today is coin, to invent a new word. Okay, and so the divergence at the center of the cube will be flux over volume. That would be the center of the R par. Bad. The divergence evaluated at the center of the R par ratio of that flux to the volume as the volume goes to zero, but that's really what we've been doing here because we only kept the first order terms. So implicitly that amounts to saying we're letting the volume go to zero here so that we can throw away all the higher order terms. They'll become smaller and smaller compared to the first order term. So you just divide through by dx dy dz and you get, aha, dvx dx plus dvy dy plus dvz dz. And so in other words, you get exactly what we said last time you got without motivating it. The ratio of the flux to the volume in the limit as the little volume goes to zero is in fact in Cartesian coordinates just the sum of the partials of the components of the vector field. And so there is now much happiness and joy. And remember that that's what you get if you dot the operator del with the vector v. The symbolic operation of that dot product, and that's the expression for div v. And so there's widespread outbreaks of smiling everywhere. Very good. I like it. You know, it'd be really effective if everyone turned to the camera. That would be silly. So.
The camera can only see.
Yeah, that's sad.
Who is it?
There you go. All right.
Will.
Have you guys ever talked about flux in terms of fluid mechanics before? No, not really. You might, well, maybe, I don't remember it.
Hey, what kind of stuff have you talked about?
I don't know.
Take your time.
Yeah.
Because flux and fluid is not talking about it.
Right, it certainly shows up in hydrodynamics, but I don't think I did that in your essay. I don't remember. Yeah, I mean, I would do it some, certainly.
We may have done it.
Yeah.
We talked about flux.
Yeah, certainly talked about flux.
And we talked
Well,
about like.
but in any case, you guys haven't done hydrodynamics before, so it comes down to, right? You haven't talked about flux of velocity and so forth, volume and all that sort of thing. Is that true? Not true? True. Okay, so in that case, let's give a physical interpretation of flux. Now, certainly, in this class, we'll be talking about flux of electric field, flux of magnetic field. But it's good to see what flux means if you're talking about fluids flowing in some volume. Even if you talk about electric and magnetic fluxes, it's still useful to understand the fluid analogy. And in fact, Maxwell and his contemporaries thought in terms of fluid mechanics because fluid mechanics had been developed before electromagnetism, and they actually thought of electric fields and magnetic fields as being little vortices within the fluid of the ether. And so this is historically very interesting too. Yes?
Does flux freezing have anything to do with fluids, or is that just the magnetic
No,
field?
that's only referring to the magnetic field really, although since it's magnetohydrodynamics that it arises in, they are linked together. But it doesn't quite, but that's a good point. A physical interpretation of flux. Okay, so we can consider a fluid, a continuous fluid, and what sorts of things are fluids, by the way? Is this a fluid?
Yes.
Yes. Yes, a blackboard is a fluid.
Ask Chad.
Yes. Chad, is a blackboard a fluid? That's right, Chad. They are foolish, aren't they? Okay. Is what Nick is drinking a fluid?
Yes.
Is what Nick is breathing a fluid?
Yes.
Yes, right. Fluids are liquids or gases or
He
plasmas.
also just seriously asked me Blackboard was the fluid. Blackboard just seriously asked me.
Is the blackboard a fluid? Right.
He was 100% serious.
Way to call it.
Okay.
Next time you ask a stupid question, you answer, you say something.
I will.
5 minutes from now, you guys won't believe it.
Let us clarify. And so, YouTube audience. A fluid is something which can flow, so therefore the blackboard is not a fluid, basically. Solids are not fluids, basically just about everything else is what it comes down to. So, you do that, yeah. Your Vita Yasser here.
Oh, yes,
See,
we knew
look
you
at
knew
that.
it.
What about,
Which is funny.
what about glass? Because
What?
that's not a solid, then glass is like a fluid.
Yeah, glass is a
It can
fluid, yeah, it is,
slowly-
because it very slowly
Oh,
flows,
you
as a
know.
matter of fact, right, yeah, if you look at cathedral windows that are centuries old, the glass is thicker at the bottom because it's been slowly flowing to the bottom, so it's actually a very slowly flowing fluid. Yep. Okay, velocity field. The velocity of the field of the fluid, v of x, y, z. That's the velocity of the fluid at every point, basically. Is v of x, y, z, and we want to know what can we say about the flow of the fluid through some surface embedded in it. So, what I want to do is consider some little piece of area. So I've got some volume here within the fluid, and there's fluid flowing through the surface of this volume. And so we can imagine that, gee, that probably involves some sort of flux integral. There's a little patch of area with unit normal n hat pointing towards the outside, and surely the velocity of the fluid through that little piece of surface has something to do with how much fluid is flowing through that piece of surface. And so what I'm going to do is, since it's hard to draw this in 3 dimensions, at least for one of my limited artistic ability, here is some area dA jutting out of the page. So, in other words, it's drawn as a line, but it's really sticking out of the page here. This is a little rectangular area sticking out of the page. And so there's n hat So n hat times dA would be the little area vector of it. And let's say that the fluid is flowing with some velocity v at that location. Then consider then the amount of volume of fluid which will flow through that little patch dA in time dt. So that fluid moving at velocity v off in this direction sweeps out a little a parallel pipe head. I guess we could just call them pars, but I don't know, I like par better, or rectangular parallel. But this one's not, this is just a general parallel pipe head. All the sides are parallel in pairs to one another. And so in other words, we can draw something like this. We can say that in time dt, then this parallel pipe head of fluid flows through area dA there. So this is really something which is sticking again out of the page. It's not just in the page like that. And so vdt would be the distance, the length of this here, because in time dt, then if the fluid is moving at velocity v, v dt is the total distance it travels. Time dt. And if this angle theta is the angle between n hat and v, then v dt cosine theta, written sideways not that well, is the altitude of that parallel pipe head there. The volume of fluid flowing through dA in time dt is going to be v dA cosine theta times dt, because v dt cosine theta is the altitude and the base has area dA. So base times altitude is the volume of a parallel pipe head, and so therefore v dA cosine theta dt is the volume of the fluid. But v dA cosine theta is, in fact, v dot dA times dt, because v dot dA is, of course, v times dA times the cosine of the angle between them, and dA is n hat times dA. You know, dA as a vector is n hat times little dA. Okay, does that make sense? So a little chunk of flux of fluid, basically. V dot dA dt is the volume flowing through at that time. So the rate of flow of volume through dA is v dot dA. You divide through by dt to get the rate, and you get v dot dA for the rate of flow of fluid through that volume. Through that little patch of area. So the net rate of flow through the whole surface is going to be what? Don't look at your notes. What's the net rate of flow through the whole surface? If v dot dA is the piece of flow through that little patch of the surface, what do you get for the whole surface put together? Integral, yeah, just integrate over the whole surface. It's v dot n hat dA, which is the flux of v through the surface. So for a fluid described by some velocity field, the flux of that velocity field through any surface is the rate of flow of fluid volume through that surface. So there's a direct connection, a direct physical meaning of flux when you're talking about the velocity of some fluid. Okay, any questions about that? If you multiply by the density, mass per unit volume, and take the flux of rho v, in other words, then you're finding the flux of mass through the surface, the rate of flow of mass of fluid through the surface. In other words, to get the rate of flow of mass through the surface, you multiply the volume flowing through the surface times the mass per unit volume. In general, the density could vary from place to place, but rho v dot dA integrated flux of rho v, in other words, is the flux of mass through the surface. Okay, does that make sense? Any questions about that? And if a fluid is incompressible, that's one whose density won't change. So what about air? Is air an incompressible fluid? No, I mean, if you get a bicycle pump, you know, or whatever, you can certainly change the density of the air in the pump by pushing on it. How about water? Well, is there any, yeah, well, okay, is there any such thing as a truly incompressible fluid? No, but how about water? Do you think it's got a reasonable approximation to be incompressible? If you put a bunch of water in a cylinder, it's awfully hard to compress it significantly. And so things like, liquids are often very nearly incompressible, even though there's no such thing as a truly incompressible fluid. And if the density cannot change, well, that means that the total mass inside any given volume cannot change as a result of flow of fluid into or out of that volume. Because, assume that water is incompressible and you're inside of a swimming pool, then pick some volume inside the swimming pool, and there's water flowing inside the swimming pool. Well, what's the total mass of water inside a given volume? Well, it's just the density of water times that volume, no matter how the water is moving. Water can move all you like, but if its density can't change, then the mass inside any given volume is just the density of water times the volume. So, in other words, incompressible fluids have the property that there can't be any net flux of mass through any surface, because if there was a net flux, the mass inside that surface would be changing. So the total mass going in and the total mass going out have to balance one another. Any surface entirely within it, there can be no net flux of mass through it. Now, if you drain a swimming pool, obviously you're changing the mass inside that volume. But I'm talking about any volume which stays completely submersed within the fluid can't have any net flux of mass through it, because otherwise the mass inside would be changing. But the mass is always the density of the fluid times the volume. Or in other words, the flux of rho v is 0. Rho v dot dA is equal to 0 for such a fluid. But by the divergence theorem, remember that the flux of a vector field through a bounding surface is equal to the integral of the divergence over the volume that's enclosed by it. So in other words, by the divergence theorem, that flux is equal to the divergence of rho v integrated over the volume bounded by the surface. And since this is true for any volume you like whatsoever inside the fluid, the only way for this integral to always give you 0 is if the divergence is equal to 0 at every point within the fluid. So div rho v is 0 for an incompressible fluid. So what that means is that if you're inside of a swimming pool, for example, since water is nearly incompressible, if I'm inside of a swimming pool, there's no way you can have a surface where the velocity is everywhere outwards at every point on that surface. Why not? What would happen if the velocity were everywhere outwards at every point on this surface? What could you say about the mass inside that surface? It has to be decreasing, right? Because fluid is everywhere flowing out of it. Similarly, the volume, you couldn't have the velocity pointing inwards everywhere on the surface because mass would be increasing. Mass would be flowing into it. So it must be true that there's some places where there's some places where the velocity points inward and other places where the velocity points outwards. For any surface, it always has to be true. There's both inwards and outwards flowing water at different points on the surface so that the total amount of mass inside the surface stays the same. V has to point in at some points and out at others. On the other hand, it certainly is possible to change the mass of water inside of a swimming pool. There are two ways to change the mass of water inside of a swimming pool. There are three ways to change the mass of water inside of a swimming pool. Instead of thinking of the third one. What are three ways to change the mass of water inside of a swimming pool? 4 ways. Well, they're all kind of similar. Anyway, yes? You could drain it, right? So you have a drain at the bottom or on the side somewhere. Okay, so that would decrease the mass. You could also decrease the mass by poking a hole in, but that's really a drain because it's just going to pour out of the hole basically. Yeah. What's that? Yeah, boil it. I was thinking that was when I said three-way. You just let it evaporate basically, you know, just let the water evaporate. You could also increase the mass. How would you increase the mass of water inside the pool? Yeah, you can't think of it anyway, huh? All right, Chad, can you help us out here?
Chad says rain dance.
Chad says ring dance. Chad, you are so silly. What a joker. No, Chad. A puppy peeing in the pool. Well, that would work, but it's not a good solution. Let's not go with that. Chad is really obsessed with puppies. You know, yeah. Gosh. Yeah. So, Chad, do you go to puppywar.com a lot?
What is puppy?
You get pairs of puppies and you have to choose which one's cuter.
Oh, you showed, never mind.
Yeah.
I have to listen to this video.
Yeah.
We need that break.
And then there's also kittenwar.com.
The kitten war is cuter.
Kittenwar is cuter, I would say. Kittens are more consistently cute than puppies are. Puppies are very, very cute when they're cute. But they're not always cute. You know,
Yeah,
certain
right.
breeds of dog, not so sure.
Drooling.
About only judging the
Yeah.
physical beauty here.
But along with Chad's idea of, you know, the puppy here, let's make it a little more sanitary and submerge a hose in the pool, you know. That would work too.
Great idea.
That would work too, yes. And the thing to note here is, okay, here's a pool. And since it's a pool, of course, you have to draw a ripply surface on top. And I've got a hose sticking down into the pool. And you can kind of imagine some kind of contraption on the end of the hose. It really wouldn't look like this. And, you know, some gentle flow, appropriate contraction. You can imagine a situation where you could get, even though this would be hard to realize in practice, water flowing neatly at constant speed, radially outwards from every point of the end of the hose contraption. So the velocity field looks something like that. What does that remind you of? The little bitty source which has field lines pointing out of it at each, you know, direction. What's that look like? What?
Charged particle.
Yeah, charged particle, yes. It looks like a charged particle. It looks like the electric field of a charged particle. By convention, a positively charged particle. Now, if we reverse pump on the hose here and suck fluid in, you could imagine fluid flowing inwards instead, and that looks like the electric field of a negatively charged particle. Now, the difference is that in the real world here, there's going to have to be water flowing in through the hose to balance the water flowing out through the end of the hose here. So if I draw any volume around the end of the hose, it's still true. V has to point in at some points and out at others. In this case, it's pointing out at most points, but that's balanced by a rapid inflow through some little part of the surface where the water's flowing through the hose into it. So there's still no net flux through this surface here. And yet, the volume of the total water in the pool is going to increase. You know, so the overall water level will rise. But the idea here now is imagine that we could pipe water in from another dimension so that we can dispense with the hose having to actually, you know, stick through the pool. Come in through the fourth dimension, and all we can see in our universe is the water flowing out of what? And so we can imagine an idealized source pumping water in from another dimension, and that's what electric fields of charges look like. It's like, you know, fluid flowing in from another dimension or out into another dimension or something like that. And that's really what's happening. No, that's part of it. Okay, so you hear enough about string theory, you might almost believe me when I said that. And now that's the modern theory. I could get you guys really going on that, but it actually isn't, it turns out. Okay, time to take a break.
So technically, that's a Can we just say that it was coming from 30 dimensions to save us that a lot of trouble?
I agree.
Okay, yeah.
Tape rolling.
Tape rolling, okay. To Today's lecture is sponsored by Coke. It's the pause that refreshes.
They should pay you for that.
I think they should.
So
Oh,
this is
no,
Ron
it goes on
from
YouTube, I think they have.
Good thing that.
So, anyway, we have this nice analogy then between an incompressible fluid and like electric fields here. So, charges are like sources or sinks of fluid, and Steph is still.
I'm fine. We're good.
Okay.
I enjoyed the chuckle of that.
So charges are like fluid sources and sinks, only the fluid is coming in from another dimension or going out to another dimension, which I kind of like. On the other hand, what about magnetic fields? Is there such a thing as a magnetic charge that we know of?
Monopole.
Right, yes, a monopole. As far as we know, there aren't any monopoles, right? So, magnetic field is divergenceless, as we will certainly see. For the magnetic field, it's always true for any surface. The magnetic field has to, for any closed surface, for any closed surface, the magnetic field has to point in at some locations and out at other locations because there's never any net flux of the magnetic field, which is because of the fact that there are no magnetic charges. So a charge is a place where field lines begin or end. Magnetic field lines don't begin or end. They're always closed loops because there are no magnetic charges. But the electric field is not like that. There are closed loops. Charges. You know, sources and sinks basically of field. And let's see. What was I going to do next here? Right. So is that the point I wanted to make? Yes, that is the point I wanted to make. Okay, so then onwards and upwards here. The director's thinking, oh man, he's blowing his lines.
This is ad lib.
Yes, it's all ad lib, that's right.
That's fine.
Yes, that's fine. It's part of the charm of this little program.
Treat this as a reality show.
As a reality
As a
show.
reality show.
That's kind of frightening. Right.
I think
So for our fluid here, the divergence of rho v is 0 outside of sources or sinks, and not so at sources or sinks if we could get the things to come in, you know, from another dimension like that. Well, jumping ahead, but touching base with something that you've already seen in Physics 111. Gauss's law for the electric field, written in differential form, is that the divergence of the electric field is equal to rho over epsilon naught, where epsilon naught is 8.85 times 10 to the minus 12th power Coulomb squared per Newton meter squared, which is called the permittivity of free space. Rho is the electric charge density as opposed to the mass charge density. And in electricity, basically, then the electric charge serves as a source of electric field. Where there is charge, the divergence of the electric field is 0. And that means that that is serving as a source of electric field, similar to the way that our little hose from another dimension serves as a source of fluid, if you will. And If rho is equal to 0, if you're in an area that's outside of charges, then the divergence is equal to 0. Just like in our fluid, if you're outside of a source or a sink, the divergence is equal to 0. So, the next thing to point out is that we can put this into a form that you would have seen in Physics 111 by using the divergence theorem. If I integrate over some volume, div E, integrate div E over some volume, by the divergence theorem, that's equal to the flux of the electric field through the surface, which encloses that volume. But meanwhile, div E d tau by Gauss's law, written in differential form, is the integral of rho over epsilon naught over the volume that is in question. Epsilon naught's a constant and pulls out of the integral. So I integrate the charge density over the volume, thereby giving me what? If I add up density times volume over the whole volume, I get the charge enclosed. Yeah, you just add. Did you look at your notes? Damn it. You just knew a Gauss's law. Well, that's cool too. Okay, right. But be sure you realize this is, in other words, density times volume is little element of charge, right? Rho d tau is dq, a little element of charge. So if I add up all the dq's inside the volume, I get the total charge enclosed. So I get q enclosed, charge enclosed by that volume, divided by epsilon naught there. So in other words, going with the differential form of Gauss's law is the integral form of Gauss's law, that the flux of the electric field through any surface is equal to the total charge enclosed by that surface divided by epsilon naught. So these are entirely equivalent expressions. One is the differential form of Gauss's law, the other is the integral form of Gauss's law. And one implies the other in a virtuous back and forth implying whatever. There's that ad-libbing again, kind of flow.
Harmony.
But that's okay.
Harmony.
What's that? Harmony. Yes, there we go. In a virtuous harmony. Right. Right.
Just hope this doesn't get on YouTube.
I don't think it will. I'm pretty conscious of that.
Make us
I
blind.
right.
There's people out there who want to watch this.
That's right. Yes. Yeah, that's right.
Doc, I think it's like, we should make the table.
Yeah.
What do you think?
Maybe if I like strap on 3 years, or something like that or something.
No, that will be weird overload.
Right. Yes. Yes. All right, you then.
We don't want me to just strap on the bunny ears anyways and walk around during the class, that'd be great.
That'd be just fine. Yeah.
Every day you're a different animal.
That's right. The curl and Stokes' theorem. Earlier we saw that if some vector field V can be expressed as the gradient of F, or some scalar f, some scalar function f, then we found that B dot dl is independent of path. Doesn't matter which path you take to get between 2 points. Or equivalently, that the integral of V around a closed path, B dot dl is equal to 0. Remember, those are equivalent, because a closed path can be thought of as 2 open paths, one going out and another going in. And if the total integral is 0, that means the going out and the going in are equal and opposite, which means 2 going out would be the same. A quick summary of all of that. So those are entirely equivalent to one another. Question? Given B, is there some test which will tell us if V has these properties? Some way of knowing that V is in fact expressible as a gradient and has path independence. If it's a force, is there some test that will tell us that the force is conservative? Ask it how it voted. And the answer, of course, is no, so we're done. Actually, the answer is yes. Why, yes, there is. After all, why would I have brought this up? The condition is that curl V equals 0. So my approach here is a little different from the notes. I'm just going to jump ahead and give you the answer and then kind of work to it. You know, and also, you know, for the divergence, we went through the steps of deriving what the expression is. Well, that's all in the notes. I go through the steps of deriving the expression for the curl, but we're not going to do it in class because it would just take too much time. So I'll give it to you to read it in the notes, how to actually come up with the condition that we'll find, and then you'll achieve enlightenment, and there'll be much smiling and so forth. But it won't be coordinated smiling, it'll just be individual smiles. And so I'll be thinking about how wonderful that'll be, that at moments I won't even know it, people are smiling because they just realize how to get the curl. All right, so anyway, now that I've come back from my little curl V, we've written it as del cross V. Well, that's awfully suggestive. So if I wanted to calculate del cross V, what would I do? I'd make V a little determinant, right? And the top row of that determinant would be x hat, y hat, and z hat. Yes! That's right. Oh, man. And the middle row of that determinant would be kind of, it's yeah, the partials, right? Partial, the partial with respect to x, because the components of the gradient vector are the partial derivative operators. So the partials with respect to x, y, and z. And the third row would be dx, dy, dt, yes. And so the x component of the curl of V is equal to what Corey said. Yes, exactly right. You just do the operations. You just say partial of Vz with respect to y minus partial of Vy with respect to z. That's right. You do that creepy thing. goes, watch this, watch this,
Oh no!
this minus this. dvx dz minus dv dx.
Just don't do
Why
it.
would you do that?
Don't do it, Chad.
It was either that or make this minus and flip it
Exactly.
around.
Yeah.
No, no.
That's being normal.
Oh, no, it isn't.
Ooh, you got someone.
And then, of course, dy by x and dx by y. Yeah. So that's how you calculate the curl in Cartesian coordinates. In other coordinate systems, it's messier. But the idea is that take your vector function, find its curl, ask yourself the following question. Actually, asking the curl is, curl, are you 0? And if the curl says, why, yes, I am 0, then you say, wow, you know what, V, I can integrate you around any path and I'm going to get 0. And furthermore, if I go not around a closed path, I'll get the same thing no matter what. And so it's easy, basically, to find out if V can, if it has those properties. It's a very easy thing to check. You just find the curl, just take these derivatives. It's all very mechanical. So, hooray! What does the curl mean? So, what is this curl beast anyway?
Clearly not known.
Well, what we want to do is imagine some surface. And you partition that surface up into a bunch of little patches. And the way I got it drawn in the notes there, the surface appears to be planar. It's in a plane, but there's no need for that. The surface can be any arbitrary, soap bubbly looking monstrosity that you like whatsoever. And what we do is we imagine then one of these little patches on the surface, which has its little outward normal n hat. And we say that the curl of V dotted into n hat, and I've just written it as curl because we're pretending we don't already know how to calculate it, and then you derive that it is in fact equal to del cross V. So curl of V dotted into n hat. So some little patch on the surface, here's my little n hat at that location. Curl of V dotted into n hat, by definition, is equal to the limit as the area of the little patch goes to 0 of the ratio not of flux to volume like we did for divergence, but of line integral to area. So in other words, we take the line integral of V around the little path which encloses dA, take the line integral of V around that little bounding path with our little area element there, and divide that by the area of the little element, and say that is curl of V dotted into n hat. And there's a right-hand rule involved here. what do you think the right-hand rule is? How would you state the appropriate right-hand rule here? Well, you got this n hat, right? And you have to have a direction that you're going to traipse around the path bounding the surface. So, gee, okay, if there's a right-hand rule, I bet I'm going to point my thumb in the direction of n hat. And then I'm going to, no, pop like a bunny. Then I'm going to go around the path in the direction of the curl of my fingers, basically. So, in other words, hey, this is how you do it.
Why does your thumb go in n hat direction?
Just cause.
That's where it gets me.
What's that?
I can't do the right hand rule.
Why not?
Because it changes.
It's changing.
So the black
Okay,
part's
you
a
need to
fluid,
find,
eh?
you need to find like a path direction, you know you have to follow your fingers.
Right.
So your thumb must point in the direction of something.
You let your fingers do the walking, and then your thumb points in the direction of the n hat. And
But
it
in other
just
cases
does.
where you're following a path, then your thumb points in the direction.
Wait, but is
But
it,
that's-
oh, this is Tuesday, yeah, so right.
Like you
You'll
can
get
for a
it, you'll get it.
vector, like for a vector, you want where your thumb's pointing. If you want where like a direction, you always follow your fingers. So in this case, you want a direction of a
I'll just try.
Just look at the kittens. Look at the kittens.
Every single time I use the right hand rule, I have to ask.
And this is where you have to go back.
Well, I guess the point is, this is a right hand rule. You know, there's no such thing as the right hand rule. This is yet another right hand rule. Okay? So, yet another right hand rule.
Because like
That's right. Car makes it's another right hand rule. All right. Anyway, so that's the definition we're making, and we're basically asserting that this curl V beast is a vector, and that this is a well-defined limit, and we're not going to prove it. We're just going to assume it's true because it is. And mathematicians have in fact proved that this works out. That's nice, isn't it? So we'll take a pair of patches here, and Ben will use his supervision to magnify the patches. Yeah, that's right. And now Ben will demonstrate supervision.
Just stand on that place,
All
right?
right, got that in there? All right, excellent. I was going to suggest that maybe Chad could see Ben's reflection in my glasses.
Not quite.
Not.
Excellent.
So the idea is there's two little patches there, and we've zoomed in on them, and we'll decide to traipse around these patches. That's a good word too. Traipse around these patches counterclockwise for each individual patch there. So I make a double-sided arrow on the middle one, because on the middle line here, because in other words on the top patch, traipsing counterclockwise means go to the right, but on the bottom patch, traipsing counterclockwise means go to the left. So, and then, if we're going to do that, that means that my n hats are coming out to shoot us in the eye, right? In other words, it's the arrow coming at you, so we draw the circle dot to represent it. So there's our two n hats there. And the crucial point here, and then, as I said, I'll let you go through the rest of the argument at your leisure, but the crucial point is that we can think of taking the line integral around the whole path, bounding the outside here, as being a sort of symbolic sum of traipsing around the top path, finding that line integral, and traipsing around the bottom path, finding that integral, PA, the total, the path around the two patches, P sub A, where you don't go to the interior line there, and this is P1 and this is P2, so path A and path 1 and path 2 there. If I find the line integral around P sub A of B dot dl, that is in fact equal to the line integral around path 1 of B dot dl plus the line integral around path 2 of B dot dl. And the reason for that is that along this common border we have something similar to what happened with fluxes. In other words, with fluxes, the flux in and out through the common border between two volumes canceled. And here what cancels is the line integral of V, because on the top patch I'm tracing to the right, and so V dot dl is whatever this dl looks like, and then on here I'm tracing it to the left. So in other words, V dot dl is opposite for these two paths. For these two parts of the paths, the part that's in common, the top of one patch, the bottom of the other patch, which is the same thing, V dot dl is equal and opposite. Along this part of the paths. So when I add up these two line integrals, these two contributions are equal and opposite, and all I get is the rest of it. This plus this plus this plus this plus this plus this, which is the whole thing around. Okay, does that make sense? Am I talking sense here? Everybody filled with happiness? Okay, thumbs up. All right. And that means we can apply this logic to this whole beast of lots and lots of patches here. So the idea is then that if I find the line integral around this outside path here, I can get that by adding up the line integrals around all these patches inside because of this pairwise cancellation around common boundaries. So the line integral around the whole outside is what I get by adding up all the line integrals around all the individual patches. So notice on the inside there's lots and lots of cancellation going on. The only things that live in the final summation is the stuff around the outer boundary of the whole surface there. Of the surface, the outer boundary of the surface. So if we apply that logic to the whole surface, what we get is that the line integral of V around the outer path, so P will be the path around the whole surface there, around that whole boundary there, is equal to the sum over all the patches. So we just label the patches with an index I. The sum of over all the patches of the line integrals around each patch, path P sub I line integral, B dot dl. Add them all up. But wait a minute, we define the curl of V such that that line integral is equal to curl of V dot n hat times the corresponding area. So curl V dot n sub I hat, the outward normal to patch I, times dA sub I, the area of patch I. That's how we define the curl. It's the ratio of the line integral to the area. So the line integral is the curl dot n times the area. And then we do the same thing we did with the divergence theorem. In the divergence theorem, we let the volume shrink to 0. Here we let the little areas of all the patches shrink to 0. So as all the dA sub I go to 0, becomes an integral. And we get Stokes' theorem in all of its glory, which says that the line integral around any closed path of v dot dl is equal to the flux of curl v over that surface, curl v dot n hat dA, which is the same thing as curl v dot dA written as a vector there. So the line integral of v around any closed path is the flux of the curl of v over any surface spanning that is spanned by that path. Or now I can't remember which way you say it. Does the surface span the path or does the path span the surface? Well, damn, whatever. Still, it's just this surface that has this boundary around it. I'll say it in a way which is unambiguous. The flux of V for any surface which has P as its boundary is equal to the line integral of V around that bounding path. So in other words, if here is some path in three-dimensional space, I could find the flux of the curl of V through that surface or through that surface. It doesn't matter. The flux of the curl of V through any surface which has our path as its boundary is equal to the line integral of V around that path. And again, remember how we derived that, the argument behind it. It happens, that works out because it's always true that on the surface itself, all the little patches, their line integrals cancel out because of that cancellation along common borders of each of the patches. So the shape of the surface ends up not mattering because no matter where you are on the surface, all those little common borders are going to cancel out their line integrals, and all that matters on the end is the border of the entire surface where there isn't that cancellation because there isn't any patch next to the border. The border is where there aren't any patches next to it causing any cancellation of the line integrals around it. And given then that this is true, given Stokes' theorem, well then, if the line integral around the path is equal to 0, if that happens to be true, well, that means that the flux of the curl of V, I'll just write it as curl V dot n hat dA this time for variety, the flux of curl V is equal to 0 for any surface bounded by P. And the only way that can be true if it's going to work for any possible surface is for curl V to be 0 everywhere. So this is our glorious conclusion that if we define this curl the way we did, then the curl of v being 0 is equivalent to line integral of v around any path is equal to 0 and vice versa. And having defined the curl of v as being curl v dot n hat is the ratio as the area goes to 0 of the line integral divided by the area of a little patch, the next step is to make a little patch, calculate what the line integral around it is, divide by the area dy dz of the patch, if it's a parallel to the yz plane, or dx dy, or whatever, take your various directions you could have. Go through an argument similar to what we did for the flux to derive the expression for the flux. It's in the notes. We're not going to do it in class, but it's in the notes. And when you go through that argument, the expression you get is the one that we already gave, namely that the curl of v is those combinations of partial derivatives. You just look at the x direction, y direction, and z direction in turn, go through the derivation, and you find the limit works out to be exactly what we found. And therefore, we achieve happiness and joy. And in fact, because of this relationship to line integral over area there, what that means is that a field which has curl is in some sense rotational. There's rotation in that field. And if you go to fluid mechanics and think of velocity fields, then a flow which has non-zero curl is one in which the velocity field kind of has field lines, if you will, that make little circles, or at least make little closed paths, so that something inside that fluid, like a little paddle wheel, would be set into rotation by the fact that, like, if here's a little paddle wheel, if the velocity is here, 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 if the velocity is such that you're going to get line integrals around paths, then it's going to make things want to curl around. And that's why in German, curl v is called rot v, to indicate that it's a measure of the rotation of the field. So curl for fluid mechanics measures tendency towards rotation. The little paddle wheel can be sort of used as a little curl-o-meter, so to speak. Drop a little paddle wheel in the flow, and if it starts to spin around, that flow has curl. And if it doesn't spin around, that flow does not have curl. So can you think of an example of something in, say, electricity or magnetism, of a electric or magnetic field which would have a curl? Yeah.
Polarized.
A what?
Like for polarized.
So you're talking like a polarized electromagnetic wave kind of thing?
Yeah, sure. In chemistry, like what do they call it? Compound twist light as it goes through.
Let me think. That you're right. That would end up having a curl. Yep. The electromagnetic field vectors in that situation of a circularly polarized light wave will in fact have curl to them. So that would be one example. Can you think of a static example? An example from electrostatics or magnetostatics? Okay, I'll give you a hint. Magnetostatics. Think of a magnetic field which has a curl. Yes?
Oh, the one around with wire.
Yeah, right. Think of a wire, right? If I've got a wire which has some current flowing out of it, what's the magnetic field look like? Circles around it, right? B, circles around it. So at each point, the magnetic field itself is tangent to the circle, so it's B, 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 B. That certainly has a non-zero line integral around it because B dot dl is always in the same direction, and so the integral is not 0. And therefore, this is a B that ain't got no curl. I mean, that does have curl, stop it, that has curl. I mean, I guess 0 is curl too, but yeah, this has curl. In fact, you may recall that the line integral of B around the closed path is equal to mu naught times the enclosed current. Does that sound familiar from Physics 111? Or at least there's something in your brain that remembers that, right? This is the integral form of Ampere's law. There must be a differential form of it as well. Well, by Stokes' theorem, I can replace the integral of B around the path with what? What would Stokes' theorem say? So the line integral of B around some closed path, Stokes' theorem says I can replace that with an integral over a surface bounded by that path. And so it would be the integral of what over that surface? Curl B. So I can say curl B dot dA, the flux of curl B over that surface is equal to mu naught I enclosed. And jumping ahead a bit, we can talk about current density. Such that the current through a surface is the flux of the current density through that surface. So just as we can talk about the flow of mass through a fluid as being the flux of rho B through a surface in the fluid, we can do the same thing with electric current. We talk about the flux of the current density, and the current density is in fact just the charge density times the velocity the charges are moving, instead of the mass density, which would be the mass density times the velocity at which the fluid is moving. We do the same thing with electric charge and talk about it flowing as a current, and then we define what's called the current density. J is equal to rho B, where rho is the charge density. The flux of J through any surface is the current flowing through that surface. So I enclosed is just the flux of J through the surface bounded by whatever path was used in the original line integral here. And since this is true for arbitrary surfaces, this means that the differential form of Ampere's law is that curl B is equal to mu naught J, where J is the current density. So just like we had an integral and differential form of Gauss's law, there's also an integral and differential form of Ampere's law. One implies the other. They're just two ways of saying the same thing. Whether you want to think big and macroscopic or little tiny differential. So it depends on which voice you want to use. You can either use Ampere's law or Ampere's law. And on that note, we're done.